Hi, thank you so much for watching my talk and AIChE. I'm going to talk to you about the work that we have done recently on understanding the effect of multivalent cations on the heterogeneous freezing of water, so ice nucleation. Let's start with why we're interested in this problem and what is so challenging about studying this kind of a problem. So we really got interested in this problem in our conversations with scientists who do climate modeling. And they told us that, um, because so little is known about heterogeneous ice nucleation, that it becomes one of the biggest source of uncertainty in their models. This got me very interested and very curious, and I started to dig into the literature more to understand what makes this problem so difficult to solve. And here I'm showing you a collection of data that demonstrates the challenge with this kind of a problem. So here I'm showing you an example of a dust. And you can see that that dust comprises of various different types of particles. You have mineral dust, you have organic carbon, you have biological particles, salt, and soot. Now, if you take these particles and look at how they affect ice nucleation, then you can get some data that looks like this. So here you, for the purpose of this talk, just look at where these bands are relative to 0 degrees C. So the further away they are, the poorer they are as nucleators. So you can see that some biological particles are good nucleators. Mineral is not as much relatively, and then soot is somewhere in between. Now, if you take this mineral and zoom further, which is what this data is showing, it's a composition of an example mineral, dust, and you see that you have many different types of particles. You have quartz, feldspar, calcite, illite, kaolinite, etc. And you can do the same thing is you take these different types of mineral clays and you look at how they affect ice nucleation. And that's what you're seeing in the data here. So now here, because it's in Kelvin, what you're going to look at, the further away it's from 273, the poorer it is as a nucleator. So you see that feldspar is a good ice nucleator, but these red diamonds, which are basically mica surface, is not a good nucleator. So based on all of this, it's natural to think that, well, if I looked at all these surfaces, and if I figured out what is similar about the good nucleators versus the bad nucleators, then I should be able to tell some of the design rules for surfaces that are good ice nucleators. So people did this, and initially they hypothesized that if the water likes the surface, and if the surface can template an ice structure, it'll be a good ice nucleator. Turns out that these design principles do not really work very well. In fact, you cannot use them to design or even predict whether a given surface will be a good or a bad ice nucleator. So this is essentially the grand challenge in this field, and this is the problem we want to solve through our research as well. So we have two key questions we want to answer. One, how do various surface properties affect ice nucleation? And two, can we develop methods to screen ice nucleating agents? Now we do this by studying a variety of different surfaces. So we've studied AGI, kaolinite, but today in these short few minutes, I'm going to talk to you about our very recent work on understanding ice nucleation on mica surfaces. So this work was really motivated by our desire to bridge experiments and simulations. Typically, experiments on nucleation are very, very difficult to do because the length scales and the time scales that one needs to probe are very hard to reach in experiments. Also, many of the surfaces that are studied are typically not defect-free. So they have defects, and these defects make a lot of a difference on the ice nucleating behavior. On the other hand, experiments can probe the length and time scales required for nucleation. Although it's hard, we can kind of do it. And we study very pristine, very clean surfaces. So now bridging these two becomes super difficult. And this is what we wanted to do. So I approached my collaborator and very good friend, Dr. Will Cantrell, and I told him, look, you study ice in experiments, I study ice in simulations, we have to find a way to bridge. So the first thing we wanted to do was find a surface that lets us study the same thing in experiments and simulations. So what does that mean? We wanted the surface to be atomistically smooth so that we don't have defects which would make it really hard to bridge experiments and simulations. And two, we wanted to probe the same property in both experiments and simulations. So we wanted to change the same thing in experiments and simulations. And so after a lot of thinking, we decided that surface should be mica. And here is why. So here I'm showing you the structure of mica. And you can see that it has like Al and silica atoms, which are connected through carbon atoms. And then these layers have ions in between. So really, it's these cations that are holding these layers together. And you can literally peel one layer out just because of the way this crystal structure is created, right? And when you do that, what you do is you expose a surface like this. So again, you have the silica, oxygen, etc. But now on the top, you have the cation. In the naturally occurring mica, this cation is usually potassium. So the one thing to note is when you peel these layers off, you get atomistically smooth mica. So it's defect-free. So criteria number one is satisfied. Now, it turns out that in experiments, you can also wash the surface with various salt solutions, and it can result in an exchange of the ions. So you can exchange the potassium for different ions. Now, we can do this in simulations as well. So now we can really probe the effect of the same property, both in experiments and simulations. And so criteria number two is also satisfied. And therefore, we said, this is a good system for the synergistic study that we want to do between experiments and simulations for heterogeneous ice nucleation. So that's what we did. Our experimental collaborator used droplet freezing experiments using cold stage. They studied various types of ions. They looked at potassium. They looked at three different divalent ions, so strontium, calcium, and magnesium. And then they also looked at Al3+. In our simulations, we primarily did simulations of water molecules on mica surface, and the two cations that we probed were potassium and calcium. The reason we stuck to just these two ions is mostly from a force field limitation perspective. All right, so let's see what are our results. So here I'm showing you the nucleation rate versus temperature obtained from the experimental studies. And you can see that here is the results for potassium. This is for divalent ions, and then this is for the trivalent ion. And you can see as the charge valence is increasing, the nucleation rate is increasing. So this tells us that the heterogeneous nucleation rate increases with the valency of the exposed ion on the mica surfaces. So now obvious next question is, why are we seeing this effect? So there can be various reasons that are leading to this effect. One can be contact area. So it's possible that when you change these cations, you change the contact area between the water droplet and the surface. And if the contact area changes, the nucleation rate could change. But the nucleation rate that I showed you is on a per centimeter square basis. So we've already normalized by the area. Therefore, the contact area change does not account for these trends that we're observing. So this is not a factor. Now, you could also have surface roughness. So ice nucleation is very sensitive to surface roughness. So now it's possible that as I'm changing the ions, I'm changing the surface roughness, which means that the potassium mica might have a different surface roughness relative to magnesium mica. So to probe this, we did AFM experiments, and I'm not showing you the results in the interest of time, but we find that there is no significant difference in the surface roughness between the different mica. So this also does not explain the trends that we're observing in the nucleation rates. So then another and the last reason that is possible is the cations themselves, right? And what might be happening is that the cations are changing the structure of water that is in contact with the surface. And so now we wanted to probe this. This is super difficult to do in experiments. And so therefore we do this through simulations. And this is where you see the synergy of the experiments and simulations. So I'm going to show you a set of results that are key to sort of our hypotheses of what's happening on mica. And I'm just introducing you to some of the terminology that I'm going to use. So I'm going to show you results of the clusters of hydrogen bonded water molecules. And basically, I'm going to show you the distribution of their sizes. And then we're going to characterize water in the interfacial layer. So whatever is within some cutoff distance of the surface, we call it interfacial water. And within that interfacial water, we characterize them as being part of first hydration shell, second hydration shell, or free water. So what we mean is if that water molecule is within the first hydration shell of any ion on the surface, it's a first hydration water. If it is part of the second hydration shell of the cation, then it's second hydration layer water. And then if it is not part of the first or the second hydration shell, we refer to it as a free water. All right, so here I'm showing you now the probability of observing clusters greater than some given size for the potassium and the calcium surfaces that we study. What really intrigued me about this result, and in fact it was unexpected, was that the potassium are showing a higher probability of observing larger clusters. This really surprised me because what I was expecting to see was that the calcium will have higher, or a larger number of larger sizes of cluster, because the logic was if something is nucleating ice faster, then they should have more clusters of hydrogen bonded water molecules, and these clusters should be big because they are going to help with the critical nuclei to form. And so that's why we were expecting that the calcium will have a larger cluster size, but these results were completely contrary to our intuition, as it often happens in research. So we said, okay, what is going on? Now, visualization is a very, very valuable tool for us computationalists, right? So here, I'm showing you snapshots of the clusters that we identified, and we looked at many of them. I'm just showing you snapshots here. And what we did is we colored the water molecules based on being in the first hydration shell, second hydration shell, or being free water. And what really jumps out as soon as you see this is, hey, there's a lot more cyan for calcium than for potassium. And we said, this might make sense. Why? If you think about it, water molecules in the hydration shell of ions are very restricted in their orientations. But to form an ice structure, you need water molecules that are free to orient and adapt these structure that is favorable for ice. And so even if you have a large cluster, but if they're all very tightly bound to the ion, then chances are they're not going to be able to take ice-like structures. And maybe that is explaining why, even with large clusters, potassium is not a good ice nucleator. So we quantified this further by calculating the fraction of free water in the interfacial region as well as within the clusters that we were observing. And we found that indeed the fraction of free water is higher for calcium compared to potassium. And in fact, the difference is even more apparent when you think about the free water in the largest clusters. So the picture that comes from this is that the free water is important. Now we wanted to also see if this same logic will hold for trivalent ions. Now we don't have good force fields available for Al, so that's why what we decided to do was take the original ions, the potassium and calcium, and simply change the charge on them. So we increase and decrease the charge of the same ion. And here I'm showing you now the results for calcium with plus charge, +2, and +3 charge. And you see that as we increase the charge, the probability of observing larger clusters is going up. But more importantly, the fraction of free water is also increasing. So you can see that this is almost 35% of the water molecules of Ca3+ are free waters. And here you can see that through visual snapshots as well. This is for Ca+. And if you see Ca2+ and Ca3+, you see a lot more cyan for Ca3+. You also start seeing these ice-like entities. So like, for example, this hexagon, this sort of bilayer-like structure, this sort of defective hexagon are very typical of an ice structure. So you start seeing, maybe you're forming ice. All right, so now based on this, we see that free water is important and that free water is taking ice-like structures. But two very obvious questions jump out, right? Why do fewer ions lead to larger sizes of hydrogen bonded water molecules and clusters? And why are there more ice particles in mica surfaces with ions of higher valency? Is the bare mica surface helping? So when we say bare mica, we really mean those regions on mica that are devoid of the ions. So to test this, we created two hypothetical surfaces. We are going to call them K3 shift and Ca3 shift. And really what we did is we took the ions on the surface. Initially, they were distributed throughout the surface in a random manner. But for these shifted cases, we just moved them to one region, and we created a large region which was devoid of all ions. But we maintained the surface neutrality. And then we performed similar simulations. And here I'm showing you now snapshots of the largest clusters that we observed. The color coding is similar for the first, second hydration water molecules, and the cyan is the free water. But in addition to this, the yellow water molecules are the ice-like water molecules. And you observe two key things. One, the clusters form in the bare mica region. And two, there's a lot of yellow particles, so ice-like particles in this. We see a very similar trend if you look at Ca3 shift as well. You see that you have a lot of free water molecules. The clusters are on the bare mica regions, and then you also have ice-like particles. So this tells us that the bare mica surface is promoting the formation of hydrogen-bonded water molecule clusters, as well as it's promoting ice-like structures. So, we quantified this, we compared Ca3 and Ca3 plus shift. We see that larger clusters are formed for Ca3 shift as well. We have looked at number of ice-like particles, etc., and all of those, fortify what we are saying here. So when you put all of these results together, what does this tell us about ice nucleation on mica? It tells us the following. Large water clusters are forming via hydrogen bonding on these surfaces. The water molecules in the ion hydration shells anchor the clusters, so they kind of help with them being long-lived. Then as the charge increases on these cations, there's a higher fraction of free water in the clusters. And these free water molecules are free to reorient and adopt ice-like structures. The regions that are devoid of ions, which is growing when you increase the charge on the ion, help with promoting the cluster formation and ice-like configuration. And it's all of these factors that are coming together to promote ice nucleation on mica when you have these higher valency ions. So that's the mechanism we are hypothesizing for the mica surface. I have a lot of other things here, but I'm going to skip them in the interest of time. And I'll go straight to the acknowledgements. I would like to acknowledge my collaborators, Dr. Will Cantrell at Michigan Tech, who did all the experimental work, and it was his graduate student, Nurun Nahar Lata, who did the work. And then also Jiaran Zhou, who is my graduate student, who did all the work related to the simulations. And we also acknowledge the funding from NSF. Thank you so much for listening to this talk, and I hope you enjoyed it.